Good morning to all. Myself Ajith Suresh, and I am here to present our work titled Swift, Super Fast and Robust Privacy Preserving Machine Learning. This is a joint work with Nishat Koti, Mahak Pancholi, and my advisor Arpita Patra of Indian Institute of Science, Bangalore. Machine learning is one of the fastest growing research domains today, and it has showcased its applications in several areas such as automobile, healthcare, finance, etc. A machine learning algorithm, in general, can be divided into two phases, training and inference. During training, several data owners come together and collectively train a model. Once the model is properly trained, it is used to predict the output for new queries. This is often referred to as machine learning as a service. Several companies such as Amazon, Microsoft, IBM, and Google provide these ML services. One of the key factors that determine the quality of the model obtained is the amount of data it used for training. The more the data, the better the model will be. But what about the privacy of the data? In a traditional ML model, the data from several data owners are collected into one place and the model is trained using the entire data in one shot. This leads to a breach of privacy with respect to the individual data. And this work focuses on ensuring the privacy of the individual data in machine learning algorithms while simultaneously allowing computations on the data. Now, let me introduce you the technique of Secure Outsourced Computation, or in short SOC. Here, the computation is offloaded to a set of dedicated powerful servers. One of the key features of an SOC setting is that it enables an average end user with a low-end system to avail the benefits of computation. Moreover, SOC solves the issue for large population as well. The parties choose a small representative set either within themselves or hire externally and assign them as computing servers. The parties then distribute their inputs among these servers in such a way that no server alone learns the input. The key desired properties of an SOC setting are: first, privacy. The data of end users should remain private. Next is efficiency, that the computation should happen efficiently with minimal computation and communication. And last, robustness. The end users should obtain the final output always. For this, we use Secure Multiparty Computation Technique, or in short MPC. MPC, a wonderful idea introduced by Andrew C. Yao in 1982, allows a set of n parties to jointly compute some function on their inputs without revealing them. The two desired properties of MPCs are as follows. First is correctness, that states the parties should obtain the correct function output. Next is privacy, that states nothing more than the function output should be revealed. The problem would have been much simpler if all the participating parties are honest. However, in reality, this is not the case and some of the parties are corrupt and they may even collude. To capture this, we introduce the notion of an adversary who takes control over the corrupt parties. There are several traits with which an adversary can be classified, and one such trait classifies the adversary into semi-honest and malicious. A semi-honest adversary is curious but is guaranteed to follow the protocol. However, a malicious adversary can arbitrarily deviate from the protocol. Another classification is based on the number of corruptions. First one is honest majority, where majority of the parties are assumed to be honest. Next is dishonest majority, where all but one can be corrupt. Depending on the security guarantee of the underlying protocol, we have mainly three classifications. First is abort, where the adversary can make an honest party abort during the execution of the protocol. A stronger security is security with fairness. Here, the honest parties are guaranteed to obtain the output whenever adversary obtains the output. However, adversary can still make the honest parties abort in this setting as well. The strongest notion is of guaranteed output delivery, or in short, GOD. Here, the honest parties are guaranteed to obtain the output irrespective of the adversary's behavior, and this security is desirable in most of the practical systems. Now we will see the details of our Swift protocol. In Swift, we focus on MPC for small number of parties. Specifically, we provide protocols for 3 and 4 servers in the outsourced setting. The setting is nice due to its efficiency and simplicity. Our protocols are designed in the honest majority setting. So for both 3PC and 4PC, we can tolerate at most one malicious corruption. We achieve the strongest notion of guaranteed output delivery. For obtaining practically efficient protocols, we resort to the pre-processing model. Here, the protocol is cast into two phases. The first one is pre-processing phase. We perform all the input independent computations in this phase, and this phase is relatively slow and expensive. Given the data from the pre-processing phase, once the actual input kicks in, a super fast online phase is executed. The table summarizes the communication cost of our multiplication gate. For 3PC, we incur the same communication as that of Blaze, the state-of-the-art practical 3PC protocol, while improving its security from fairness to guaranteed output delivery. The work of Boyle et al. Requires only a communication of just 3 ring elements in the online phase. However, the communication cost is applicable only when several million multiplications needs to be computed together. Also, they use distributed zero-knowledge proofs in the online phase, making the online phase relatively slow. Coming to 4PC, we have a 2x improvement over the state-of-the-art GOD protocol of Flash, and are on par with that of Trident that provides only the weaker security of fairness. Coming to privacy-preserving machine learning, we provide efficient instantiation of several building blocks. One among them is dot product, which forms building block for most of the ML algorithms. The dot product of two D-length vectors x and y is given as sum over 1 to d xi times yi. For the 3PC case, we achieve a communication cost completely independent of the feature size for the first term. And for the 4PC case, our results are similar to that of multiplication. Other building blocks include truncation, comparison, bit-to-arithmetic conversions, etc. Now, I will provide the details of a primitive introduced in this work named joint message passing, or in short JMP. JMP allows two senders with a common value to communicate the same to a receiver in such a way that either the receiver obtains the correct message or the parties jointly agree on a trusted honest party among the parties. When viewed as a functionality FGEM, the functionality accepts input from both the senders, let's say M from sender 1 and M dash from sender 2. If M is same as M dash, then it conveys the message M to the receiver. In case if the messages are different, then the functionality computes the identity of a TTP among these three parties and conveys the identity to all the parties. In the case of a TTP identification, the parties proceed as follows. The parties send their inputs in clear to the identified TTP. The TTP performs the computation using all the inputs and obtains the output in clear, and the output is sent back to all the parties. Now, we see the 3PC JMP primitive in detail. Here, there are two senders S1 and S2 and a receiver R. The sender S1 is passing the input as message M, while S2 is having the input as message M dash. In first step, S1 sends M to R, while S2 sends a hash of M dash to R. Now, R checks if the hash of message M is same as the hash received from S2, and it sets a bit we call as inconsistency bit to 1 if the hashes are not matching, else the bit is set to 0. In the next step, the receiver R conveys this bit to both S1 and S2. Now in the third round, both S1 and S2 mutually exchanges the bit that it received from R. Once the bit exchange is completed, party S1 updates its inconsistency bit to 1 if it has seen a bit that is set to 1 from either S2 or R in the previous steps. Similar for the case with party S2 as well. Now, the parties for which their inconsistency bit is set to 1, they will broadcast the hash of their messages. Here, party S1 broadcasts hash of M, S2 broadcasts hash of M dash, whereas R broadcasts hash of M, where M is the message received from S1. If the hashes broadcasted by S1 and S2 are not matching, then we put them in a conflicting set and we can safely assume the receiver R to be the TTP. If the broadcasted values of S1 and S2 are consistent, then we will check the values among S1 and R. If they are not, we assume S2 to be the TTP. And if they are also matching, then we will assume S1 to be the TTP. The detailed analysis appears in the full version of the paper. To summarize, in first round, S1 and S2 sends message M and the hash of M dash respectively to R. In the next round, R communicates a bit B back to S1 and S2, and in the third round,
S1 and S2 mutually exchanges the bit B received from R. We split the JMP into two phases. The first one is send phase, where the communication from S1 to R in the first round will only be executed. The rest of the steps, as you see, are used as part of verification, and the remaining steps are categorized as a verify phase, as they are used in verifying the correctness of the communication from S1 to R. And the good thing about this split is that the verify phase can be deferred till the end of the execution protocol and can be done together for all the messages that are communicated by the same S1 S2 pair towards the R. For the case of jump for 4 parties, in addition to the 3 parties, we have a 4th extra party. Here, the senders input their messages M and M' respectively to the jump functionality. The functionality first checks whether the messages are same. If yes, it will convey the message to the receiver. If not, we know that one among these 3 parties, sender 1, sender 2 and receiver, is corrupt, and we can safely assume the 4th extra party to be the TTP. Hence, the functionality conveys the identity of the 4th party as the TTP to all the remaining 3 parties. In this work, we benchmark the training and inference phases of logistic regression algorithm as well as the inference phase of deep neural network. The benchmarking is performed over a WAN network simulated using Google Cloud instances. The table 7 and 8 shows the results for our 3PC NN inference and the 4PC NN inference. Thank you for listening to my talk, and I am happy to answer any questions.